Hello guys, in this series of learning data structure topics, we are here to explain you about the Avl tree. The Avl tree was introduced by Russian mathematicians G.M. Edelson, Wilsky and E.M. Landis in 1962. Hence the name Avl tree was kept. Avl tree is a self-balanced binary search tree in which the difference between the heights of left and right subtrees of every node in the tree is either -1, 0 or +1. This difference is called the balance factor. The balance factor can be reduced by the formula height of the left subtree minus height of the right subtree. The figure here shows how the tree is balanced. If you notice, every node has the value 0 or 1, which is the correct value of balanced tree to be an Avl tree. Every Avl tree is a binary search tree, but all the binary search trees need not to be Avl trees. When it comes to Avl trees, rotations are the most important topic. A rotation is the process of moving the nodes to either left or right to make the tree balance. Rotations are of two types, either single rotation or double rotation. Single rotation usually is further divided into left or right, and double rotations into left right and right left. Single left rotation or LL rotation moves every node one position to the left from the current position. In the first figure, you can see how the balance factor is -2, which isn't acceptable in case of Avl tree. So we move to the element 1 to the left so that the tree became balanced and all the balance factor becomes 0. Next is the single right rotation, also known as RR rotation, in which every node moves one position to the right from the current position. In the first figure, you can see how 2 is the balance factor of the element 3, which is not the condition of Avl tree. So we move the element 3 to the right so that the balance factor becomes 0 and the tree becomes balanced. The left-right rotation is a type of double rotation in which first we move the element to one position to the left and then to one position to its right. In the tree, you can see how the balance factor is 2, -1 and 0. To make it balanced, first we move the element to the left and then to the right so that the balance factor becomes 0. Next is the right-left rotation, in which first we have to move the element to the right and then to the left. In the figure, you can see how the balance factor is -2, 1 and 0. When we move the element 2 to the right, it becomes -2, -1 and 0. Then we move the element 1 to the left and so it becomes 0, 0 and 0. Hence, the tree becomes an Avl tree. When it comes to operations, we can perform 3 operations on an Avl tree. First is search, second is insertion, third is deletion. Search in an Avl tree is performed exactly in the same way as such in a binary tree. Due to height balancing factor of Avl search tree, its complexity is log n. The example, here in the tree, suppose we have to search a value 45. First, we will start from the root node. As 25 is much less than 45, we move to the right subtree of 25. The first element on the right subtree of 25 is 50. So we compare 45 with 50. As 45 is less than 50, we move to the left subtree of 50. The first element of left subtree of 50 is 35, which is less than 45. So we move to the right of 35. The right subtree of 45 contains 44, which is less than 45. But to move further, we have to have a subtree, but 44 does not have a subtree. So we conclude that 45 is not present in the above binary search tree. Hence our searching is done. When it comes to the second operation, it is called insertion. In an AVL tree, the insertion operation is performed with O log n time complexity. The AVL tree inserts a new node as a leaf node. The searching operations can be performed in the steps as follows. First, we insert a new element into the binary search tree using any simple insertion logic. Second, after insertion, we check the balance factor because the whole dependency of an AVL tree lies in the balance factor. So if the balance factor is either 0, 1 or -1, we go for the next operation if there is any. And if not, as in the balance factor is not 0, 1 or -1, we perform the rotations we studied earlier and make the tree balance. For example, we have to insert the numbers 1 to 8 in the search tree. First we insert 1, that's why its balance factor is 0. When we insert 2, its balance factor is -1 and 0. When we insert 3, the balance factor becomes -2, which is not acceptable. So we move the element 1, which has the balance factor of -2, to the left so that the tree becomes balanced. Furthermore, we insert 4 and this tree is still balanced. When we insert 5, the balance factor becomes -2, which is not acceptable. So we perform the left rotation again and the tree is balanced. In the same way, we insert 6, 7 and 8. In this figure, you can see how the tree is balanced as it has either -1 or 0 values as its balance factor. The deletion operation in AVL tree is similar to the deletion operation of binary search tree, but the important thing to note here is that we have to check its balance factor after every deletion. In this case, you can see how if we delete 20, we can see that 20 does not have any child, so it is deleted simply. Second, if we delete an element 30 which has only one child, then it pays no attention. Third is the deletion of node having exactly 2 childs, in which we have to further check whether the tree is balanced or not. The advantages of AVL tree is that it is much faster than the red-black tree. This means the users are able to compare their task much quicker if they rely on other such operations. Balancing capabilities. As AVL tree is a self-balanced tree, which means it does not take any longer to process informations. In an AVL tree, we can also include search, delete and insert. Thank you.